Okay, so let's discuss how to find the probability for the union of three events. All right, and this proof, in the idea that we're going to use to show this proof is pretty much the same idea that you would use to show that the probability for the union of two events is equal to the sum of the two probabilities minus their intersection. Now that I have three events, you see that it's the sum of their individual probabilities minus their intersections, and then we add on the intersection of all three. So minus their pairwise intersections, and then adding on their the intersection of all three. But the idea is the same, but it's obviously it's going to be more complicated than if we only had two events that we were trying to find the union of. All right. So I will warn you that this is a long proof, and I would recommend that if you're trying to follow along, that you also write it down yourself as you're following along. But if this is something that you want to be able to do, it's kind of a fun proof to kind of work through. All right. Quick thing about notation: I'm not writing my intersection sign, so I write union, which is like a U. Intersection is not really being written, so just something about notation. When I write AB, probability of AB, what I mean is the probability of A intersection B. All right, the intersection sign is this upside down U, and when we have two events that are written next to each other, we just assume that intersection is there. Okay, so that's just kind of statistician, lazy notation. All right. Okay, so let's get into the proof for this guy. Okay, so my Venn diagram, when I have three events, so I would have A, B, and C. All right, so let me clearly label this. This is A, B, and C. Events A, B, and C. Okay, so this area here, this area right here, this is where A is and where B is not. So A intersect B complement, and where C is not. So C complement. So this is where A intersect B complement, C complement is. Okay, this area right here. Similarly, okay, right here is where let me start with A. So it's where A is not, so A complement, where B is, and where C is not, C complement. Okay, so that's where this area right here is. And down here, this is where A is not, so A complement, B is not, so B complement, and where C is. Okay? All right. Then when we move in right here, so actually just right here, not going into the inside there, this is where we have A and C, but not B. Right? So A is here, B is not, so B complement, and we also have C. All right. So here, where we have C and we have B, but A is not. Okay. So A complement, B and C. All right. And then right here we have A, we have B, but we are not including C. So A, B, not C. And then lastly here is the intersection of all three, A, B, and C. All right, and I probably should have used a different color for that. So A, B, and C. Okay? All right. So when I need to find, what do I need to find? I'm looking to find the probability of A union B union C. In other words, I need to find the probability of each of these little disjoint areas that I just created. All right, so I need to find the probability of this first area here, A, B complement, C complement, union, okay, this area right here, A complement, B, C complement, all right, union, this area here, A complement, B complement, C, okay, and then I'm going to scroll down. Then I have the union of each of these here. So I'll start with A, B, C complement, then union, A complement, B, C, and then union, A, B complement, C. All right, then lastly, I have the union of the inside, A, B, and C. Okay, so you see how many little pieces did I break that into? I broke it into 1, 2, 3, 4, 5, 6, 7 different pieces. Right, so like if I was doing a proof for only the union of 2 events, this would be much simple, right? Because I would have 1, 2, 3 pieces to break it into. But now that I have 3 events, it's now 7 pieces that I get broken into, right? I have 1, 2, 3, 4, 5, 6, and 7. Okay? Actually, let me use numbers to kind of create a little bit of a shorthand here, because rewriting each of these a million times, it's going to get really complicated and nasty looking. So let me call this A, B complement, C. I'm going to call this 1. Okay? So this is 1. This is going to be 2. And this is going to be 3. Then here's going to be 4. Here's going to be 5, 6, and then lastly 7. Okay, so using this new shorthand, this is equal to the probability of 1 union 2 union 3 union 4 union 5 union 6 union 7. Okay, so it's just these numbers are representing what's written here, but I just want to use them as shorthand. Okay. Now note that each of these, A, B complement, C complement, and then A complement, B, C, these are all disjoint, right? And I've purposely broken them up like that. So since they're disjoint, so these are all disjoint, I can change this union, knowing properties of probability for disjoint events. This union can just be a sum. So this is equal to the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4, 5, 6, and 7. All right. Okay. So now I need to figure out what each of these probabilities are. Right? So let us start with A, okay? The probability of A. What is the probability of A? It's the probability of each of these little pieces. 1, 4, 6, and 7, okay? So the probability of A is the probability of 1, 1, 4, 6, and 7. All right. Now I'm going to rewrite this. I'm going to solve for the probability of 1 so that later I can plug in for the probability of 1. Because remember, we can't find each of these individual probabilities that I've broken out, 1, 2, 3, 4. Rather, we do know the probability of A, we do know the probability of B, etc. Right? So the breaking out these 1, 2, 3, 4, 5, 6, 7 is merely for the purpose of this proof. But in reality, we need to come up with a solution that has probabilities that we actually know, which are the probability of A, probability of B, probability of C, and then their intersections. Okay, so let's go ahead and solve this for the probability of 1. Okay, so this will be the probability of A minus the probability of 4 minus the probability of 6 minus the probability of 7. Okay, so I've just done algebra, where I basically have taken all of this and brought it over to that side, and using subtraction, I've solved for the probability of 1. All right, let's do something similar for B. So what do I have for B? I have 2, 4, 5, and 7. Okay. So for B, I have the probability of 2, 4, 5, and 7. All right, so now let's go ahead and solve this for the probability of 2. This will be the probability of B minus 4, 5, and 7. All right, and let's do the same thing for C. For C, which groups do I have? I have 3, 5, 6, 7. All right, so the probability of C is the probability of 3, 5, 6, and 7. All right, so then when I solve this for the probability of 3, I would get the probability of C minus the probability of 5, 6, and 7. All right, so I'm going to go ahead now and plug in this guy, and this guy in here. 1, 2, and 3. Okay, so what do I have when I do that? All right, so on the left-hand side, I still have the probability of A union B union C. And now on the right-hand side, instead of probability of 1, I'm going to write out all of this stuff. So probability of A minus the probability of 4 minus the probability of 6 minus the probability of 7. Okay, now instead of 2, I have the probability of B minus the probability of 4 minus the probability of 5 minus the probability of 7. All right, and then lastly, instead of 3, I have the probability of C, the probability of 5, the probability of 6, and the probability of 7. All right, so now I still have this back material, so I still need to write that, plus the probability of 4, 5, 6, and 7. Some cancellation occurs, so let's go ahead and do that. This guy can cancel with that guy. 5 shows up here, 6 shows up there, and 7 shows up there. Okay, so let's see what I have. So right now, let's go ahead and pull these probability of A, probability of B, and probability of C out front. Okay, and then I still have minus the probability of 4. I still have minus the probability of 5, minus the probability of 6, and I have 2 7s, so minus 2, the probability of 7. Okay, all right, so now I still need to figure out what's the probability of 4, 5, and 6. So let's scroll back up. Let's look at those guys. So you see that they are in partly in these union of 2 event areas. Okay, so let's go ahead and start with the union between A and B. Okay, so, sorry, not the union, the intersection. They are in this intersection of A and B area. Okay, sorry about that. So let's go ahead and start with finding the intersection between A and B. All right, so the intersection between A and B has the probability for this this 4 area and this 7 area. Okay, so the probability of 4 plus the probability of 7. All right, let's go ahead and solve that for the probability of 4 so I can plug that in later. Okay, this is going to be equal to the probability of A and B minus the probability of 7. Okay. Okay, now let's move on to the next pairwise intersection, right? What's this intersection here? This intersection would be between B and C. So this intersection right here that I've marked in green is BC. And BC has 5 and 7 in it. Okay, so the probability of BC is the probability of 5 plus the probability of 7. If you were to solve that for the probability of 5, then we would have probability of 5 equals the probability of BC minus the probability of 7. All right, and then let's do the last pairwise intersection, which would be, let me use this right here. And who is that intersecting between? That is the intersection between A and C. A and C. Okay. Probability of A and C. And I scrolled away too fast. I didn't see what. So what is that? That's 6 and 7, right? So that is the probability of 6 and 7. When you solve that for the probability of 6, you get the probability of 6 equals the probability of AC minus the probability of 7. All right, so now I'm ready to plug in each of these guys. So I have 4, 5, and 6. 4, 5, and 6 right there. So that's what I want to go ahead and plug them in. Okay. And what do I get? So on the left-hand side, I still have the probability of the union of 3 events. Okay, on the right-hand side, I still have the probability of A, the probability of B, the probability of C, right? I just copied what you see here. Okay, now I have minus the probability of 4, right? Which was the probability of AB minus the probability of 7. Okay, then I have minus the probability of BC minus the probability of 7, and then the minus the probability of AC minus the probability of 7, and then lastly at the end I still have this minus 2 probability of 7. Okay, so let's go and distribute these minus signs. Okay, that makes this minus probability of 7 a positive. So I still have probability of A plus the probability of B plus the probability of C plus the probability of AB. Oh, that's a mistake. That should be minus the probability of AB, right? Because this minus here, minus the probability of AB, and then now it's plus. This minus and a minus makes a plus probability of 7. Minus the probability of BC, and again, the minus and the minus makes a plus probability of 7. Okay, then I have minus the probability of AC, minus and a minus makes a plus. Okay, minus 2 probability of 7. So I have 2 probability of 7, and then how many probability of 7s do I have over here? I have 3, right? So there's some cancellation here. So 2 will cancel with 2 of these guys, and I'll have just 1 left. All right, so let me go ahead and rewrite what I have. I have the probability of A, the probability of B, the probability of C, the probability of AB. I'm going to leave this for the last thing. So, oh, and I did that again. It should have been minus. Let me change that. Minus the probability of AB. Okay. Then I have minus the probability of BC. I have minus the probability of AC, okay, and then lastly I have the probability of 7. Now what was 7? If we scroll back up, 7 was ABC, the intersection between A, B, and C. So instead of writing that, let's write A, B, and C, the intersection between A, B, and C, okay? And that is what the theorem said, okay? That the intersection between three events is equal to all this jazz over here. And so we have successfully proven this theorem. All right, thanks for watching.